This video shows the most recent advancement in structural AI lab by Dr. Wang Jiaji at the University of Hong Kong, the exact Dirichlet boundary physics-informed neural network or EPINN for solid mechanics. The rapid development of civil engineering requires simulating structural systems from video inputs. However, it still faced difficulties in computational cost and efficiency. This could be categorized into three problems: forward, inverse, and design. And recently, AI has proven to provide solutions to these data and physics problems. Machine learning has been integrated with solving a spectrum of problems from data-driven, physics-constrained, to fully physics-driven. While speed is a limitation in physics-driven problems, there is no traditional solver for data-driven and physics-constrained problems. Traditional finite element software mostly relies on central processing units. However, graphical processing units are designed to subdivide complex problems into thousands of separate tasks and compute them in parallel, making them ideal for machine learning tasks. The figure below shows the schematic plot of AI models from model-driven to data-driven algorithms for solid mechanics. EPINN is considered a physics-driven model that requires only small data. Physics-informed neural networks take advantage of the capability of deep neural networks as universal function approximators in the universal representation theory by Kurt Hornick in 1989. It is able directly to tackle nonlinear problems in the setting and become a new numerical solver for partial differential equations. EPINN has been developed to solve a wide range of problems. This page shows the solving process for Berger's equation. The neural network predicts the solution field of U based on input coordinates x and time t. The loss of the partial differential equation is evaluated together with data loss. While training the neural network, when the total loss reduces to a small value, the solution of the PDE is obtained. EPINN has also been used for solid mechanics problems. For this page, researchers developed EPINN for solving elastic solid mechanics problems without labeled data of the solution field. However, there are two major challenges. First, the loss function consists of the constitutive equation, compatibility equation and boundary loss, which have a different unit and needs to be scaled to find a reasonable loss function. Second, the current approach is hard to extend to the nonlinear constitutive model. EPINN has also been developed to solve Navier-Stokes equations. This page shows the flowchart of NSF nets. In 2020, Hidden Fluid Mechanics, HFM, was proposed to consider arbitrary training domain data in EPINN framework and to guide the solution of Navier-Stokes equations with limited measurement data. The inverse problem can be solved simultaneously in the training process to fit with scarce training data. EPINN has also been developed to solve other computational science and engineering problems. For example, the hierarchical deep learning neural network could be adapted to replicate the linear finite element and solve purely data-driven, limited data, computationally expensive problems. Despite all mentioned improvements, training EPINN without labeled data is still challenging. In this study, we present EPINN with 5 building features as shown in the flowchart. First, for the 1D problem, neural networks exactly reformulate the shape function of linear or quadratic truss elements, and we proved this can be formulated with convolutional neural networks, CNNs. Second, we adopt tensor decomposition for 2D and 3D problems. Third, we use the principle of least work to achieve the exact force boundary condition. Fourth, we used the exact displacement boundary condition. Fifth, we used meshless finite difference, MFD, to compute gradient information more efficiently, although automated differentiation, AD, can also be used. Firstly, this study proved that the shape function of a 1D truss element can be exactly reformulated using convolutional neural networks, CNN, exactly. When the nodal coordinates are fixed, the only trainable weights are in layer 5, which corresponds to the nodal displacement in the finite element method. Therefore, in the EPINN framework, the number of trainable parameters can be notably reduced while formulating the same shape function in both linear and quadratic 1D truss elements. Secondly, the tensor decomposition was applied in 2-dimensional and 3-dimensional cases to reduce the number of parameters as well as complications in model generations. Thirdly, the principle of least work was considered in the loss function to minimize the total work of the system. By using this formulation, there is no need to meet the force boundary condition exactly or explicitly. The force boundary condition only appears in this loss function. When the loss function reaches a minimum, the force boundary condition will be met. Fourthly, the approximate distance function was implemented to obtain the exact Dirichlet boundary condition. Lastly, meshless finite difference was applied to mitigate the influence of stress localization and control the small mesh size in 3 directions. This was found to be favorable for convergence. However, this is not mandatory as AD can also obtain the gradient information for EPINN efficiently. Let's look at the results of one-dimension truss problem. As observed in the comparison, EPINN achieved an efficient solution of a 1D truss under complicated body force and a speed-up of more than 13 times compared to conventional PINN in converging to the solution. In 2 dimensions, the EPINN solution converged to abacus simulation results within 3 minutes faster than the abacus model, while PINN does not converge after 1 hour and a half. In 3 dimensions, EPINN converges after 8 minutes of training while conventional PINN did not converge after 8 hours. Therefore, EPINN can rapidly provide the solution field of FE simulation results with similar computational time for forward problems. Compared to FE analysis, the gradient of the solution field with respect to input parameters can be obtained in real time, which is favorable for inverse problems and design problems. Currently, EPINN developed by us is focused on solving linear elasticity mechanics problems. We will further implement deep learning-based nonlinear material constitutive models in EPINN framework to achieve efficient simulation of nonlinear mechanics problems. We had already published a paper in the Journal of Computational Physics in 2022 reporting a deep learning framework for constitutive modeling based on temporal convolutional network, TCN. In this study, we summarized 2 key features and requirements for deep learning-based nonlinear constitutive models at the material point level. First is long-term history dependence, which means that the stress is updated based on ultra-long strain history. Second is causality, which means that the stress can only be updated based on previous strain history, with no leak of future information. We found the model architecture of TCN meets the aforementioned requirements and is well fit for constitutive modeling. We developed an abacus simulation database for both concrete and steel materials. The concrete dataset was generated using Tsinghua University Concrete 3D Model, THUC3, in abacus, and the steel dataset is a modified Chebyshev model. We found that TCN can be trained to predict unseen stress-strain curves of concrete and steel material with high efficiency. We also compared the performance of TCN in learning the nonlinear material law of reinforced concrete, RC, cross-section as well as the 2D steel dataset under arbitrary loading history. We will further implement TCN and other state-of-the-art models into the EPINN framework to achieve nonlinear simulation of mechanics problems. Thank you for your attention.